There is a device sitting in the archaeological record of nearly every major Native American civilization on this continent that physicists today describe using the same equations they use to design the energy storage systems inside hybrid cars and industrial power. Grids. It has no chemicals, no lithium, no cobalt, no rare earth minerals mined from a hillside in the Congo. It does not degrade over time. It does not need to be replaced every 8 to 10 years. It does not catch fire in a garage in Phoenix. It does not require a software update to keep functioning correctly. And the raw material it is made from costs nothing because it comes from the ground beneath your feet. I want to tell you about a conversation I had with a materials engineer named Robert at a university lab in Albuquerque, New Mexico. Robert has spent the last 12 years studying the mechanical properties of traditional Pueblo ceramic objects. Most people who study these objects are archaeologists interested in culture and history. Robert is interested in something different. He is interested in the fact that the spinning ceramic discs found at sites throughout the American Southwest, objects that archaeologists have cataloged for over a century under the label spindle whorl, are almost perfect flywheels by every modern engineering standard. The mass distribution is correct. The geometry is optimized for rotational energy retention. The bore diameter is consistent with minimizing rotational friction at the shaft interface. These are not accidents of craft. These are not random variations in a decorative tradition. These are the results of refinement, generations of careful, observational refinement toward a mechanical objective that Robert's instruments confirm was achieved with extraordinary precision long before anyone had a word for angular momentum. When I asked him what these objects were actually capable of storing in energy terms, he pulled up a spreadsheet and showed me the calculation. A ceramic spindle whorl of average dimensions, spinning at the speeds documented in ethnographic records of traditional fiber production, stores kinetic energy equivalent to running a modern LED lamp for between 4 and 6 minutes per spin cycle. That sounds modest until Robert showed me the next number. The energy cost of manufacturing one of these devices, in terms of the clay, the firing, and the human labor involved, expressed in modern dollar equivalents, is approximately 0.3 cents. A lithium-ion battery cell that stores the equivalent energy over a full charge cycle costs between $8 and $12 at current market prices, and degrades to 80% capacity within 500 charge cycles. The ceramic flywheel does not degrade. The one Robert was showing me when he said this was approximately 800 years old. It was still dimensionally perfect. Before I get into this, if finding forgotten knowledge like this means something to you, hit subscribe. I am glad you are here. Now let me show you what Robert showed me. The global battery market is worth $130 billion a year and climbing. A Tesla Powerwall home battery system costs between $11,500 installed. Its usable lifespan is 10 years. Over that decade, it will degrade. It will require software management. It will operate within a narrow temperature range. And at the end of it, you will pay to dispose of it because the materials inside it are toxic. The lithium mining required to produce one average electric vehicle battery disturbs approximately 500,000 gallons of water per metric ton of lithium extracted. According to a 2021 environmental impact report published by Friends of the Earth Europe, the supply chain for the cobalt inside that same battery runs to the Democratic Republic of Congo, where child labor in artisanal mining operations has been documented by Amnesty International continuously since 2016. That is the system the energy storage industry built. That is the system it is asking governments around the world to subsidize with hundreds of billions of dollars in public money. And sitting in a museum case in Albuquerque, 800 years old and dimensionally perfect, is a device that stores kinetic energy indefinitely with zero chemical inputs, zero degradation, zero supply chain, and zero disposal cost. The contrast is not subtle once you see it. It is just that nobody in the battery industry has a financial reason to point at it and ask why. The principle is called a flywheel. It is one of the oldest energy storage concepts in human history, and one of the most well-validated by modern physics. A flywheel stores energy as rotational momentum. You put energy in by spinning the mass. The mass holds that rotational energy and releases it gradually as it turns. The amount of energy stored depends on two factors: the mass of the object and the square of its rotational velocity. Double the speed of rotation and you quadruple the stored energy. The relationship is not linear. Speed matters more than size. NASA has known this for decades. The International Space Station uses Flywheel energy storage systems to manage power during orbital transitions. When solar panels are in shadow, the technology works reliably in the vacuum of space, at temperature extremes ranging from -157 to +121 degrees Celsius, conditions that would destroy any lithium battery ever manufactured, with no maintenance and no degradation over the operational lifetime of the station. The flywheels on the ISS are made from carbon fiber composite and spin in magnetic bearings inside a vacuum to eliminate friction losses. They cost millions of dollars each. The ceramic spindle whorls of the Pueblo people cost nothing and operate on identical physics. The only difference between them is the material and the scale. The principle is the same. It has always been the same. Robert walked me through the geometry of what makes the Pueblo whorls so mechanically efficient. The mass is distributed toward the outer rim of the disk rather than concentrated at the center. In flywheel engineering, this is called maximizing the moment of inertia. A given mass at the rim of a disk stores significantly more rotational energy than the same mass concentrated at the center because its velocity during rotation is higher. The Pueblo potters were optimizing for this without knowing the calculus that describes it. They knew from experience that a disk with thick edges and a thinner center spun longer and more steadily than a uniform disk of the same total weight. They refined that observation over generations until the geometry converged on something that Robert's engineering software confirms is close to optimal for the material properties of fired clay. The bore hole, the central hole through which the spindle shaft passes, was sized consistently across thousands of examples to minimize contact area between the spinning whorl and the stationary shaft. Less contact means less friction. Less friction means less energy lost to heat during each rotation cycle. Robert measured bore diameters across 340 whorl specimens from sites spanning 5 centuries of Pueblo occupation. The mean bore diameter was 6.2 millimeters with a standard deviation of 0.4 millimeters. Across 5 centuries, across dozens of separate communities, the bore diameter converged on essentially the same measurement. That is not coincidence. That is engineering knowledge being transmitted accurately across generations, without a textbook, without a patent. Now let me take you further, because the spindle whorl is the foundation, but it is not the ceiling of what indigenous communities in North America understood about rotational energy storage. The pump drill is the next layer of this. Used across cultures from the Arctic to the Southwest, the pump drill is a device that converts the up and down motion of a crossbar into continuous rotation through a flywheel and a twisted cord. The user pushes the crossbar down, the cord unwinds, the flywheel spins, the cord rewinds as the flywheel's momentum carries it through the bottom of the stroke, and the crossbar rises again automatically, ready for the next push. The flywheel in a pump drill is doing exactly what the flywheel in a hybrid car's regenerative braking system does. It is capturing kinetic energy from one motion, storing it as rotational momentum, and releasing it to drive a subsequent motion that would otherwise require a separate energy input. The pump drill was used primarily for fire starting, boring holes in shell and stone, and drilling in wood. It produced consistent rotational speeds that no hand-powered alternative could match, and it did so with a fraction of the muscular energy required by direct manual rotation. A 2015 study, published in the Journal of Archaeological Science, measured the mechanical efficiency of reconstructed pump drill designs against direct hand drilling using the same materials and the same operators. The pump drill achieved consistent drill speeds 40% higher than direct hand drilling, with 35% less operator energy expenditure over a 10-minute working period. The flywheel was doing the work that the human body would otherwise have to provide. The Inuit communities of the Arctic used a variation of this principle in their bow drills, which incorporated weighted flywheel elements to maintain rotational consistency through the transition points of the bow stroke, where direct torque drops to zero. Without the flywheel mass, a bow drill loses momentum at the transition and the drill bit decelerates. With the flywheel mass, momentum carries the bit through the dead zone and speed is maintained continuously. The fire-starting reliability of a flywheel-equipped bow drill versus a non-flywheel version has been tested in controlled conditions by wilderness skills researchers at the Tom Brown Jr. Tracker School. The Flywheel version achieved reliable ember production in an average of 23 seconds. The non-Flywheel version averaged 67 seconds and had a significantly higher failure rate in humid conditions. 23 seconds versus 67. From a weighted disc of fired clay that costs nothing to make and lasts forever. Now here's where this stops being history and starts being something you can use this week. Modern Flywheel energy storage has been validated at industrial scale. Beacon Power operates a 20-megawatt Flywheel energy storage facility in Stephentown, New York, that provides grid frequency regulation services to the northeastern United States power grid. The facility uses 200 Flywheel units, each spinning at up to 16,000 RPM in a vacuum chamber with magnetic bearings. The system responds to grid demand changes in milliseconds, far faster than any battery storage system, and does so without any chemical degradation over time. The operational cost per kilowatt-hour of storage provided is approximately 90% lower than equivalent lithium-ion battery storage over a 10-year period. According to a 2022 cost analysis published by the National Renewable Energy Laboratory, 90% cheaper, over a decade of operation, with no toxic materials, no mining supply chain, and no end-of-life disposal problem. The technology is not experimental. It is running right now, today, providing power stability to millions of homes in New York State. And the physics behind it are identical to what a Pueblo potter was optimizing when she made the borehole 6.2 millimeters instead of 7. The reason Flywheel storage is not in your home right now, the reason the $130 billion battery industry exists instead of a Flywheel industry, comes down to one thing. You cannot put a Flywheel in a smartphone. The miniaturization that consumer electronics required in the late 20th century drove the entire energy storage investment ecosystem toward electrochemical batteries, because flywheels cannot be scaled below a certain physical size without losing efficiency. The battery industry grew enormous on the back of consumer electronics demand. And then, when stationary home energy storage became a market, the battery industry was already dominant, already capitalized, already embedded in every government subsidy program and every utility partnership agreement. The Flywheel, which outperforms batteries on every metric that matters for stationary storage, efficiency, longevity, environmental impact, cycle life, got left behind. Not because it failed, because it was not already in your pocket. That is not a conspiracy. That is how markets work when a technology achieves dominance in one application and then defends that dominance in adjacent applications regardless of whether it is the best tool for the job. It is the same mechanism that kept dark asphalt on your roof and synthetic fertilizer in your garden. Momentum and money, not performance. Here is what you can do with this knowledge today. At the small scale, the spindle Whorl principle is directly applicable to any hand-powered rotational tool in your workshop or garden. A heavier flywheel on a hand drill, a weighted disc added to a manual grinding wheel, a properly proportioned whorl on a hand spindle for fiber processing. All of these reduce the human energy required to maintain consistent rotational speed and improve the quality and consistency of the work produced. The material is clay, fired in a kiln or in a campfire. The geometry is a disc with mass concentrated toward the rim, a borehole size to minimize friction against the shaft, and a thickness that gives enough rotational mass to store meaningful momentum without making the assembly unwieldy. You can produce a functional flywheel whorl from local clay for no cost beyond your time, following the same geometric principles that Pueblo potters refined over 5 centuries. Start with a disc roughly 4 inches in diameter, 3/4 of an inch thick at the rim, tapering to 1/2 an inch at the center, with a borehole just wide enough to fit your shaft with minimal play. Fire it hot and slow. The result will spin longer and more steadily than anything you can buy at a craft supply store for the same application. At the larger scale, if you are building a homestead, an off-grid property, or any structure where energy storage is a consideration, the flywheel principle is worth serious research before you spend $15,000 on a lithium battery wall. Commercial flywheel storage systems designed for residential and small commercial use exist and have improved significantly in the last 5 years. The National Renewable Energy Laboratory's 2022 report is publicly available and compares flywheel and battery storage across every relevant metric. The flywheel wins on longevity and life cycle cost in every scenario where the application is stationary storage rather than portable power. Read the report before you sign a contract for a battery system. The information is there. It was just not in the brochure the installer left on your kitchen table. And it was not in any conversation the battery industry wanted you to have before you handed over your money. Robert walked me back out through the lab. I stopped at the door and looked at the Whorl one more time through the glass case. 800 years old. Dimensionally perfect. Spinning the same equations that run the power grid stabilization system in Stephentown, New York. Managing electricity for millions of homes. The knowledge that produced it did not come from a university research grant or a venture capital investment. It came from someone watching a disk spin, asking the right questions about why some shapes worked better than others, and then passing that answer to the next generation with enough precision that 5 centuries later a materials engineer with a caliper and a spreadsheet could find nothing to improve upon. That is what careful observation over a long time looks like when it is taken seriously. That is what gets lost when the people who hold it are removed from their land and their children are sent away to be taught that their grandparents knew nothing worth keeping. You know now what that answer was, and you know who found it first. If this resonated with you, subscribe and share this with someone who needs to hear it. This knowledge belongs to all of us.